So in this video, I really want to get into some of the basic theory behind the way that graph translation and stretching and scaling works. Some of it is stuff that you guys know, and some of it is stuff you may have never seen before, but this is really interesting stuff because it gets into sort of why this stuff works the way it does. So in order to do that, I'd like you to sort of pause the video and either think about or draw on your paper, what do you think the graphs of y equals sine x, y equals 2 sine x, and y equals sine 2x look like? Once you've got those, replay the video and sort of take a look at what these look like, and we'll talk about what happened. Alright, so here they are. The first one you shouldn't be surprised about. This is the graph of sine x. It starts at 0, it goes up, comes back down, and comes up. It ends over here at 2 pi. The graph of 2 sine x really shouldn't be surprising. You guys are aware of the fact that when you put a constant in front of a function, it effectively makes the function stretch to be twice as tall. Right? So this is now going up to 2, crosses the same place here at pi, goes all the way down here to negative 2, comes back up and ends its fundamental period at 2 pi. The one that's interesting is down here at the end, the sine of 2x. I feel like a lot of people think that, well, since I multiplied a 2 on the inside, it should stretch this function to be twice as wide. This thing should take all the way until 2 pi to finish itself out. But I have a different understanding of balancing. When I look at this, when I see it, I think about the idea that, well, if I'm going to balance this equation, like let's actually think about this one. If you're trying to balance this equation, if I multiply the right side of this equation by 2, the y has to get twice as large to compensate for that. And so that's actually what's happening here. This graph, instead of going up to 1, is going up to 2 because I put a 2 over here on this side. Now in this case, when I put a 2 inside here next to the x, y can't anticipate, that's not going to make it twice as tall. In fact, the only way to balance this is to let x do the balancing. Because I put a 2 inside of this, x has to do the opposite thing. X effectively has to cut its values in half in order for this equation to maintain its balance. And so that's why the period of this graph changes. Like this one is repeating itself in 2 pi, this one is now repeating itself in pi. You get one full rotation of the graph within pi. Another way of thinking about this is this. Imagine that you were to plug in pi right here. So imagine that you were to take pi and plug it right in there for x. When you plug that in, what is now inside of the sine expression? It's 2 pi. It's like when your graph gets to pi, it thinks that it's actually at 2 pi on the graph. Your graph is going to go all the way through 0 to 2 pi, the entire curve of sine, as you go from 0 to pi. So long story short, and I know I said a lot here, but long story short, when you put that 2 inside of there, it's going to condense the function. It's going to make it half as long instead. So one other question I think I could ask here then, now that we've sort of seen that and thought about it, what then would you expect the graph of y equals the sine of 1/2 x to look like? So pause the video, think about that for a minute, and then, draw that. So sine of 1/2 x, that effectively means that, we talked about it before, in this one up here, the period was originally 2 pi, and we divided by that 2 to get that the new period of the graph would be pi. So for this one, if my original period was 2 pi, I'll divide by the coefficient 1/2 and find that the period of this new function is 4 pi. This graph will start at 0 and will repeat over here at 4 pi. Right? So we'll have 2 pi in the middle, we'll have pi in the middle of that, 3 pi here, and you'll sort of have a very slow, gradual sine graph here. It's sort of, twice as long, twice as stretched out as a standard sine graph is. Now this gets a little bit more complicated when we start talking about horizontal shifting, so that's what we're going to look at next. So I've provided for you two graphs here, right? I've already given you y equals sine x on the top, and I've already given you y equals the sine of 2x on the bottom. This again is what we saw on the previous slide, not a big deal. First, I'd like you to think about what this is going to do. I believe you should be able to answer this question based on what you learned in intermediate algebra last year. I think we all understand that when you put a minus pi over 2 inside there, this works, quote-unquote, works backward and shifts the graph to the right by 2. So I'll put that graph up here now. So here it is. Notice that, it's sort of, here's the sine shape again, right? It's just now it's starting, moved to the right by pi over 2. We talked in the previous video about, the origin, normally is here. This origin has been effectively shifted to the right by pi over 2, and it's going like this. Now in class, I may have mentioned the idea of, why? Why does this work backward? And it has to do with that balancing act, right? When I put a minus pi over 2 in here, how does x have to compensate to keep this equation balanced? Well, in order for this equation to stay balanced, in order for y to stay in the same place, in order to keep the same shape, x, if this is effectively going down by pi over 2 because we're subtracting, this is going to have to go up by pi over 2. And when we're talking about up, that means to the right. This graph is going to shift to the right by pi over 2 because that's how x is compensating for the addition of a minus pi over 2 here. Okay? So, again, you saw this in intermediate algebra last year. When you put a minus inside of the parentheses, inside of the function, it sort of works backward and shifts things to the right. If there had been a plus inside of here, it would have shifted to the left instead. So now this is where things get exciting. This is where I really feel like we can benefit from a deep understanding of this stuff. Something you did not do in intermediate algebra last year is how do you deal with a shift when there is also a 2, like when there's also a coefficient on this x. Right, so I mean, like, pause the video, think about that for a second. Think about whether you think this graph is going to, if this graph is going to shift to the right by pi over 2 because that's what we expect, or whether you think the 2 is going to have some part in it. So think about that. Maybe not write anything down, but think about it and be ready to take a look. Alright, so there it is. That is the graph of the sine of 2x minus pi over 2. So my question for you is, how much did this shift? Right? And, if we sort of stop and think about it, right, we look at the original graph of sine of 2x, and we notice that that started at the origin. This graph is clearly starting here, right? It's going like that. And I don't know that I really need to zoom in on this, but I mean, we can do that. We can get in here and look at this, right? Where did this graph start from? I mean, pi over 2 is way over here. Pi over 2 is 1.57, right? That's pi over 2, right? Where this started was here. It started at pi over 4, 0.78 or so. So the point I'm getting at here is this graph, you may have thought that this was going to shift to the right by pi over 2. It didn't shift to the right by pi over 2. In fact, this graph shifted to the right by pi over 4. Now why? And the big question is why, and I want you guys to understand this. The reason why is that when I put a pi over 2 in here, x can compensate by increasing by pi over 4. It's almost like what's happening is I'm doing pi over 2 over 2. And what's happening is that this over 2 is canceling with this 2 that's in front, making this 2x into a, pi over 2 and allowing it to cancel. Right? So long story short, and I'm going to be getting into the mechanics of this in the next video, but what's happening is that this is shifting right by pi over 2, that was the actual shift factor, divided by the coefficient of x, divided by 2. And when we simplify that, we end up seeing that it's pi over 4. We are going to be doing that every single time there is a shift when it's also compounded by a horizontal stretch factor. Now, the last thing I wanted to do in this video is I sort of wanted to go through a summary of the effects of the constants on these graphs. And this is almost all I'm going to say about these graphs. This is what they're always going to look like in general. There's going to be a constant in front of the sine. It might be 1, but there it is. There will be a constant in front of the x. There will be a constant added here, and there will be a constant added here. And each one of those numbers has a different effect, right? So the first thing we can talk about, we've already discussed it, is the amplitude. Amplitude is found by finding the absolute value of a. We talked about that in the previous video. So you just take this number that's out here in the front, this a, take its absolute value, that'll give us the amplitude. That's how far the graph goes up and down. Right, vertical shift, also very easy. We covered this in a previous video as well. Right, for the vertical shift, all we have to do is look at the number that's at the end. Right, that number at the end gives us our vertical shift. If it's positive, it goes up. If it's negative, it goes down. Not a big deal. These next two things are the new ones that we just learned. Right, so first up is period length. The period length of the function, in other words, how long it takes for the thing to repeat. Right, there are two options, and both of them depend on that c value. So the period length of your function is going to be 2 pi over c if you're dealing with sine, cosine, secant, or cosecant. And it'll be pi over c if you're dealing with tangent or cotangent, right? The period length, by the way, is how long it takes in the x direction for the function to repeat itself. So, and I want to make sure you guys understand this, what these are both doing is they're basically taking the original period of the function, which was 2 pi for sine, cosine, secant, and cosecant, and pi for tangent and cotangent, and it's just dividing it by that coefficient of x. And then the final thing we have here is this business of either horizontal shift, or it's generally called phase shift. And what it is you compute it by doing h, which is sort of that shift factor. So h divided by c. So h divided by c is going to be the phase shift amount, and it will be to the right if the value is negative, and it will be to the left if the value is positive, just the way that we think about those shift factors. Okay? So this has all just been theory. In the next video, I'm going to get into some solid examples about how we graph these things. So sit tight. As soon as we get into that video, I'll give you the step-by-step rundown of that, and we'll have a good time.